Hello students, welcome once again to our physics class. Today we are going to discuss from chapter 9, refraction at a spherical surface. Let us see a convex spherical surface. This is a convex spherical surface. This is glass. This medium is glass. We'll take it as, like before, we'll take it as denser medium 2, and this side you have air. Let us take it as medium 1. Let us draw a principal axis. This is your principal axis. Suppose this point, the optical center, we'll take it as O. Optical center is that point along which any light ray passes will just go undeviated. They will just pass straight. This way if it comes, it will go straight. This way if it comes, it will go straight. This way if it comes, it will go straight without any deviation. Or let us mark with some other letter, let it be C. If you take a point object anywhere on the principal axis, suppose let me take it as here, O. The ray that will come out from the object, it will just pass straight, passing through the optical center, it will just go straight along the principal axis. The second ray, if I draw here, obliquely this way, then it will converge, as it is a convex spherical surface, it will converge at some point here, say as I am marking it as I. Let this point be M, the point of incidence. At this surface, at the point of incidence, if you draw a normal perpendicular to that point, to the surface, then the normal passes through the center of curvature of the curved surface. This is, let it be K, the center of curvature. Or we can do even like this, K we can keep it here, this point, and we can write the center of curvature as C. So these two reflected rays, they are passing or they are intersecting each other at point I. Thereby a real image is formed at I. The angle that the incident ray makes to the normal, we call it as angle of incidence I. And the angle that the reflected ray makes to the normal, that we call it as angle of refraction, R. This angle is R. To get a relationship that exists between the refractive index of the second medium, this is mu2, then here medium 1 we are taking mu1, and the distance between the object, image and the radius of curvature. This is the radius of curvature from K to C is called radius of curvature. Then from K to I, so image distance, I am marking here V, image distance, and from O to K, that is your object distance U. There exists a relation between this R, U, V and refractive index mu1 and mu2. So to get the relation, what we do here is we choose these angles for convenience. We mark this as alpha. This angle will mark it as beta. This angle will mark it as gamma. This angle is gamma. So now from this point M, if you drop a perpendicular line here, let us say it as N. MN is perpendicular to the principal axis, that is OI. But this point N is very close to K. Ultimately at the end, this N will be replaced with K. So to start with, you can start like this. In right triangle OMN, in right triangle OMN, tan alpha is equal to, tan theta is defined as perpendicular to its base, so Mn by On, Mn by On, and this will give us alpha is equal to Mn by On. For small angles, the values of tan alpha, sin alpha, I'll write down here. For small angles, tan theta is equal to sin theta, both we take it as theta. This is our assumption that we have to take it like that. In this right triangle M and C, you can find tan beta. In right triangle M and C, tan beta is equal to Mn by Nc. This will give us beta is equal to Mn by Nc. Likewise, then gamma you can find out if you take right angle triangle M and I. In right triangle M and I, you can find out tan gamma, and tan gamma is equal to Mn divided by Ni, and this will give us gamma is equal to Mn by Ni. So first of all, you find out this one alpha, beta and gamma. Then using the concept of exterior angle property, our idea is to find out the value of sin I and sin R, I and R. So in this triangle, if you look OMC, this is forming the exterior angle I, that will be equal to sum of interior opposite angles, that is alpha plus beta, that will be equal to I. In triangle MOC, angle I is equal to alpha plus beta. Angle I is equal to alpha plus beta because I is the exterior angle of triangle MOC. Exterior angle of a triangle is equal to sum of interior opposite angles. This exterior angle property will use it, or you can write in short exterior angle property also. Like that, in this triangle, if you look MCI, beta is forming the exterior angle. Exterior angle beta is equal to R plus gamma. In triangle MCI, beta is equal to R plus gamma. So you can write from here, you can get R equal to beta minus gamma. R is equal to beta minus gamma. Like this, you can find out the values of I and R. Then by using Snell's law, of refraction, what you can do is sin I by sin R is equal to refractive index of light is passing from air to glass, refractive index of second medium with respect to first, or you can write this as refractive index of second medium divided by refractive index of first medium. Now sin also, the values are very small, the angles are very small, so in place of sin you can write I by R is equal to mu2 by mu1, or you can cross multiply first. I mu1 is equal to R mu2. Now I is equal to alpha plus beta into mu1, and R is equal to beta minus gamma mu2. Now we place the values of alpha, beta and gamma. Alpha is equal to Mn by On, plus beta was equal to Mn by Nc. This is mu1 is equal to beta, here is Mn by Nc, minus gamma was equivalent to Mn by Ni. Like this you can put the values. This is mu2. Now here Mn you can take common from left hand side as well as right hand side. Mn, if you take common, you'll have 1 by On plus 1 by Nc mu1 equal to Mn, if you take common, 1 by Nc minus 1 by Ni mu2. Now this Mn you can cancel it out, and as I said before, this point N is very close to K, so N will replace with K. Wherever you can see N, it will be On will become, On will write it as OK. So since N is very close to K, so On is nearly equal to OK. Then you have NC, NC is nearly equal to KC, and NI, NI is nearly equal to KI. So substitute in place of NK, 1 by OK, I'm putting it here OK, plus mu1 is equal to 1 by Kc minus 1 by Ki mu2. After putting this value, look, the common terms, these two are common. I'll transfer it this side, and this minus term I'll bring it towards my left. Left hand side you have 1 by, or you can write mu1 by OK. This one is mu1 by OK. And this minus term will be mu2 by Ki. Minus will become plus mu2 by Ki is equal to, here you have mu2 by Kc, mu2 by Kc is plus, we'll bring the other side, that is minus mu1 by Kc. The common terms will keep on one side. Then you'll get like this, mu1 by OK plus mu2 by Ki is equal to mu2 minus mu1, and Kc is common. So this relation is also necessary while deriving the lens maker's formula and convention. Here OK is equal to the object distance, and it is left side. This side, left side, we take it as minus. All of you will be knowing. All the distances towards our left, we take it as minus. All the distances towards our right, we take it as plus. So left side, the object distance, so you take it as negative, minus u. Ki is the image distance towards our right, so take it as plus v. And Kc is the radius of curvature, that is r, that is also on the right hand side, so write it as plus r. And if you use the values here, then you will get like this, mu1 divided by minus u plus mu2 divided by v is equal to mu2 minus mu1 divided by radius of curvature is plus r. So this one more properly, if you write, it looks like this. This is positive, so we write first mu2 divided by v minus, this is minus mu1 by u. Mu1 by u is equal to mu2 minus mu1 divided by r. So this is the final expression for a convex reflecting surface. This equation holds good for any curved surfaces. Let us solve this question. Like this we'll do. Light from a point source in air falls on a spherical surface refractive index 1.5 and radius of curvature 20 centimeter. So the light which is falling on the surface, that surface has refractive index 1.5. From here the light is coming, so you know that this is the refractive index of the second medium, 1.5, and refractive index of air, you already know it is 1. And radius of curvature is given as 20 centimeter. The distance from the light source from the glass surface is 100 centimeter. So the object distance, light source is the object here. The distance from the surface is 100 centimeter. So U is equal to 100 centimeter. Like this, you write down the values. Then you go for your question, what they want to let us find, at what position the image is formed. So they are asking you to find out the value of V. V is equal to how much? So first of all, before doing, you use the sign convention. For refractive index, no sign convention. For radius of curvature, it is given on the right hand side, so it is positive. It is plus. Object we always keep on the left hand side, so it is negative. And image will be formed on the right hand side. We know the answer should be in positive. So let us see. We know that for any curved spherical surface, mu2 divided by V minus mu1 divided by U is equal to mu2 minus mu1 divided by R. So put the values. Mu2 we have 1.5 divided by V to find out, minus mu1 divided by U, it is minus 100, equal to mu2. Mu2 again, you know the value, that is 1.5. Mu1 value is 1, minus 1 divided by radius of curvature is 20. So 1.5 by V plus 1 by 100, minus to minus is plus, equal to 0.5 divided by 20. 5 4 times is 20, 5.1 times is 0.5. So then we can transpose this value here towards your right hand side. 1.5 V by V is equal to 0.1 by 4. Is 1 by 40, you can write, remove the decimal. Plus on your right hand side, it will become minus 1 by 100. Then calculate it. LCM of 40 and 100. 10 is common to both of them. 10 4 times, 10 times. 2 2s are 4, 2 5s are 10. 5 4s are 20. 20 into 10 is 200. 40 5 times minus 100 2 times. Then will give us 1.5 divided by V is equal to 3 by 200. Cross multiply, V is equal to 200 into 1.5 divided by 3. 3 5s are 15. Then multiply, 5 2s are 10. Then 2 zeros you have. After decimal you have 1 digit. So it will come out as 100. Then we can write down the unit centimeter. 100.0, that is equal to 100 centimeter. Lens. A lens is a transparent refracting medium bound by two surfaces, of which at least one side must be curved. I am writing down here, a lens is a refracting medium, or a transparent refracting medium transparent refracting medium bound by two surfaces of which one must be curved or spherical, you can say. So this material, if it is bound by two refracting surfaces, and the material must be a transparent one, light must pass through it, should refract, then that material we will call it as a lens. Lenses are broadly classified as convex and concave. One is convex lens and the other one is called concave lens. If a lens is thicker at the middle, in this region if it is thick, and at the edges if it is small or thin, then that lens is called a convex lens. This is the cross-sectional view of the lens. If you look like this, if you keep like this, then it will appear to be circular. Actually it is circular, but you can hold it and you can feel the middle it is thick and towards the edge it is thin. Middle it is thick and towards the edge it is thin. So that lens we call it as a convex lens. This is the cross-sectional view. Likewise, concave lens also in actual practice it is circular, but if you keep it like this, the cross-sectional view, then it will appear this way. At the center it will be thin and at the edges it will be thick. If it is thick at the edges and thin at the center, then that lens we call it as concave lens. Further classification if you do, convex lenses are of three types. This is one, we call it as biconvex lens. We call it as biconvex lens. The second variety of convex lens is your plano-convex. One side is plane, one side is convex. This is plano-convex lens. And the third one comes from this convex lens. The third variety of convex lens is your concavo. This is concave and concavo-convex lens. We call it as positive meniscus as well. This is concavo-convex lens. So these are the three types of convex lens. Biconvex, sometimes we call it as double convex also. But most of the time when any person will talk about lens, when they say convex, then this biconvex only they are talking about it. And here also like that. This is called biconcave lens, but when a person will say about concave lens, then first thing this will come in your mind, it is concave lens. Likewise, concave lens are also of three types. This is your biconcave lens or double concave lens. Then second one you have your plano concave lens. This is plano concave. And the third one is your convexo concave. This side will come like this, convex, and this side it will be concave. This lens we call it as convexo concave lens. This is called convexo concave lens. So these are three types of concave lens. So this altogether you have 6 different types of lenses. But one thing you have to keep in mind, their action. These are called convex lenses are called converging lens as well. So all the three, they have got converging action. To know this, let me show you by taking one point object. We'll discuss about the terms. This line passing through the optical center. Now you may think, what is optical center? You have to know a light ray passing through that point goes undeviated. That point is called the optical center. If I draw any line passing through the optical center, it will go like this. If it comes this way, it will come like this. So that point inside the lens, where all the light rays passing through that point, optical center of the lens. And all these lenses that we are talking is about thin lenses. We are all discussing about thin lenses. To make it bigger, to visualize it properly, we are drawing it fat. In actual practice, all the lenses are very, very thin. Just you can hold and you can feel it. Just by looking, you cannot make out which is concave and which one is convex. So to see their converging action and diverging action in all the 6 types of lenses, I have drawn on principal axis here. This is the optical center. If I keep any object here, suppose A is the position of the object, then the ray which passes through the optical center, it passes straight. The second ray, if I take like this, then it will converge. So the image will be formed here. This is point object, this is point image. So this center, instead of taking O, I'll take it as C. So that object I can mark it as O. This is how image is formed in a convex lens. We'll see all the 6 different types of images formed by convex lens as well. But to learn these two, I need to show you with a point object. Now in this case also, the ray that passes through the optical center, it goes straight. But if, again I'm writing O, it should be C suppose. This is the object O. A ray that is passing from the object, if it refracts, as I said, convex. Convex means converging nature, it must have. Converging means it won't go straight, it will converge like this. But it cannot go and touch the principal axis because that much it cannot converge. Instead of going straight, it is converging. This way it will go. So the image will be formed. If you produce this line, the image will be formed on the principal axis. At this point, you will get the image. So it should look like this. It should look straight. Yes. Now it is okay. Like that here also, if I draw the principal axis, the ray that goes straight, it will go straight way. If I keep an object here, the image, the reflected ray will converge. Instead of going straight, it will converge slightly. And this one, if you produce it, the image will be formed here in concave convex lens. Like that, here, biconcave lens, they have diverging nature. If I allow a ray to pass straight, it will go straight. The second ray, if I take from the object here, point object, if I allow it to diverge, then you know it's diverging lens to go like this. Image will come here. So this behavior will be shown by these 2 lenses as well. The image will be always between the optical center and the object. It will be between the optical center and the object. And here the image will be beyond the object, behind the object. Here also behind the object. Let us see here how it looks. This is the object, suppose say O. The straight line going to the optical center will just go straight. Second ray diverging in nature. So it will go this way instead of going straight. And then image will be formed here. Likewise, in this case also, if I draw the optical center, if I draw the principal axis, if I take any object, so it has diverging nature, so it will diverge and the image will be formed here. These are the ray diagrams, especially this one we'll discuss it later also. This is for point object, but this 4, just have a closer look where the image will be formed when you keep the object in front of the lens. These two also has got converging action, and these two they have diverging action to try to go away. Thank you and have a nice day. Stay tuned with LFI Educates.